We're now going to turn to the geometry of aerial photos. Um, so the first thing to explain is that um, photos have frame capture geometry. They are frame capture sensors. That is, an entire two-dimensional area is captured at one time. Scanning systems pick up just a subset of a two-dimensional area um, at a single time. So, for instance, a cross-track scanner or a whisk broom scanner, a single pixel might be captured at one time, and then the location of that pixel on the ground is moved from one side of a swath to the other, and the brightness of those individual pixels are picked up as it moves. And a long track or push broom scanner will capture one line of the ground surface, and then as the sensor is moved forward, either on an airborne platform or a satellite platform, it will pick up subsequent lines. So the importance here is that a frame capture sensor captures one two-dimensional area all at one time, and that affects, as we'll see, the geometry of the image. So optical components of a simple camera and those of the human eye are dissimilar. That is, you have an object in the real world. Light impinges upon it and is reflected into the eye. Okay, so it passes through a lens, and the image appears upside down at the back of the eye. On a camera, you have an object, you have a lens, and the difference is that the object appears on the film at the back of the camera. Let's talk about parts of the camera that are important for this. We have the focal plane. That's where the film surface is. Focal length, or F, is the distance between the focal plane and the center of the lens. And focal length is normally 6 inches for aerial mapping, although 3.5, 8.25, and 12-inch focal length have also been used. The lens focuses light onto the focal plane, and this geometry is that of similar triangles. Okay, so we have angles that are going to be the same as they pass through the lens, and then the angles that connect the top of an object and the top of the projected object and the bottom of the object and the top of the projected object, those angles will also be the same. So these are similar triangles. And if you have two similar triangles, each one is going to be a simple enlargement of the other. Okay? So they have the same angles and their sides will be in the same proportion to the others. So these diagrams give you an idea of how changing focal length changes the images that you're going to be looking at. And nothing here is really to scale. So if you look at a scene, you imagine that you're looking down at the camera, and then you're looking at the focal plane image, which is sort of looking at the focal plane from the vantage point of the lens. So if you have a short focal length, okay, the ratios between the angles from the lens to the scene are a large multiplication of the angles and or the distances within the camera. what we call the exterior and interior orientations. So if so, you're going to be viewing a relatively large area in the world on your focal plane. If your focal length is larger, the ratio between the distances of objects and the lens are going to be moderately large relative to the distances within the camera. And so you're going to be looking at a smaller area of your scene within the focal plane. And finally, if you have a very long focal length, then the ratios of the distances are going to be even smaller, and you're going to be, zoomed in on a small portion of the exterior scene. Sugar. So as focal length increases, the size of the scene that is imaged decreases. And you can see on that top example, the distances between the lens and the scene objects is very large relative to the distances between the lens and the focal plane. And so you're going to be looking at a very large subset of whatever scene you're looking at. As that focal length gets longer and the ratio between the distances between the scene and the lens becomes smaller relative to the distances between the lens and the focal plane, you're going to be zooming into smaller portions of the scene. So we can start looking at the geometry of photos and figure out what the scale of the image is. Scale is just the ratio of the photo distance for an object to the real world distance or length of an object. Okay, so if we look at this image, we have the scene at the bottom. Okay, we have some of those geometry lines connecting objects in the scene to the lens, and then we have the negative that you would capture. So this would be past the lens. You'd have that focal length, and then you're imagining that you have a piece of film there. So the negative would have reverse tone and reverse geometry, right? Because you're flipping objects up and down and left and right. So this is the geometry of a vertical aerial photograph obtained over flat terrain. And I'll explain why we say that in a moment. So to make the geometry easier to visualize, we can flip that negative over the lens, okay, and put it in the same geometric position relative to the lens, i.e. the size of it remains the same, but you flipped it over to have positive tone and scaled geometry with so the objects on the photos are in the same position relative to the say the extent of the photos as they are in the original scene. And that kind of makes the concepts easier to understand. So let's look at scale. Scale is just the distance or size of an object in the photo over the ground distance. If you look at maps, the most popular map scale is 1 to 24,000. That's for USGS topographic sheets. So it's 1 inch to 24,000 inches, or 1 centimeter to 24,000 centimeters. If you do it in inches, you have 1 inch is equal to 24,000 inches or 2,000 feet. So that's very convenient in terms of calculations. So let's look at the other distances that we're identifying here. So we have ground distance at bottom, so the length of a bicycle. We can now see we're simply scaling to the photo distance on that flipped photo. And then as we go through the lens, we can see on the original negative, we've just scaled it and flipped it. In order to figure out what the scale is, we can either measure the photo distance and the ground distance, or we can use the ratio of the focal length to the height of the lens above the ground surface, which is just equal to the focal length over the difference between the altitude minus the elevation of the ground surface. And what makes this possible are those similar triangles. Here we see a figure illustrating the effect of elevation on scale. So we have two objects there, or two lines there, one at a lower elevation, one at a higher elevation, each one of which is 1,000 feet in distance. Okay. However, because the higher elevation, okay, has a different geometry, that is, the ratios are different in terms of the distances, okay? As a consequence, the size of the object is larger on the film. And this is straightforward in the sense that you make this correction all the time when you're simply viewing something in the real world. Objects that are closer appear larger than objects that are further away. That's all that's really saying. So what that means is you have to make a correction for elevation if you're trying to map scale over a large area with variability in elevation. And we have a process that creates orthophotography that basically takes photography where you have varying topography and corrects for these effects so that you have uniform scale throughout the entire image. So, other parts of the camera, we have the lens that focuses reflected energy on the focal plane. We have the aperture, which is the size of the hole that allows light into the camera. Larger the hole, the more light that collected. And then we have the shutter that controls the time that the camera is seeing light. Things get much more complicated from here. We have in aerial photography, we use metric cameras. Okay, so metric cameras are made to take precise aerial photography. So we have one portion that's the film magazine. So it's loaded with film that's then used. You can take the film magazine off a camera and then put another one on it. You then have the camera body itself, and then there's a separate assembly for the lens cone. And that's just put there for added flexibility. You can switch lens cones back and forth without actually changing the camera body. The focal plane in one of these cameras actually has holes in it, and there is a vacuum system that pulls the film toward the focal plane so that it's perfectly flat. The lens on a camera like this is actually multiple lenses that together give you the effect of a certain a single lens. So these are very precise, and we'll talk about parts of this camera as we move along. And one of the things I always find interesting about these cameras is it has something called a forward motion compensation device. So as you're flying, you have your shutter open for some period of time. your plane is actually, or your platform is actually moving. So that would give you a little bit of a blur to the photo, except that the forward motion compensation device actually moves the camera backwards as the photo is being exposed, so that the camera is actually staying over the same point as the photo is captured. And this leads to a high resolution, better contrast in the image spatially. And you can see from the left to the right, there's kind of a little rectangular box with lines in it. That's for measuring spatial resolution. So that's actually out in the real world. It's a sheet that has that those lines printed upon it, and you can see in the right hand with the image motion compensation, those lines come out crisper. Until recently, small format cameras, i.e. 35 millimeters or 75 millimeters, that refers to the size of the negative, have not been used in remote sensing very much. They're not metric cameras generally, so they're unsuitable for making measurements. They have short focal lengths and can't cover an area as large as a standard metric camera. However, they can be useful for photo interpretation purposes when you only need a sample of the area. And if you need more observations at different times of the year, or if you need data within a short time period and can't arrange a flight. And that's especially true when cost is a factor in terms of getting an actual photo collection. I said until recently. Now that we have drones, there's been a need for cameras that have shorter focal lengths and that are light and can be mounted on these systems. And so you have a range of cameras that are relatively inexpensive. Something like the GoPro on the right, which is about $300, or an advanced camera that's specifically designed for aerial photography that comes in around $1,500. That's not a lot of money for collecting aerial photography. And cameras like this, like I said, this is actually film that was collected using a 35 millimeter camera in natural color during the growing season, and from an altitude that allows you to cover up a fairly large area. And you can see it's a contrasting time of year. Okay, it's within the growing season, and it's being compared to a large format aerial photograph that was taken during a leaf off period during a 5 to 7 year cycle between observations. So you can see how those two things can complement each other.